Segasonicfan here, tested out my new camera mount, and I've got a cool video I think to show you all. Today we're going to be working on a oral irrigator, aka sometimes called a Waterpik or water flosser. And these are my favorite kinds of videos to do. I hope you all enjoy them, where I take something that's kind of a popular consumer item, usually from Shenzhen, the consumer innovation capital of the world nowadays. The engineers there are just so cool and brilliant. And I tear it down and show you the insides and how it's working and how you can make it better. What's so cool is that so much technology nowadays is using, a lot of similar components, like maybe even more than ever before. And so there's a lot of cool upgrades and things you can do, and I plan to do some upgrades with this. I needed to take this apart and work on this immediately because I love this thing, and it's totally helped me avoid going to the dentist for like 2 years now. What I do is and this is my claim to fame. I'm very proud of this quote unquote idea. Maybe somebody else has come up with it, but I fill the reservoir with tap water and a bit of mouthwash. And I use this as a mouthwash oral irrigator. And let me tell you, folks, it does the trick. It is amazing. But needless to say, it's not perfect. And mine actually broke after, heavy use. I'm using it 2 times a day for, I don't know, probably close to a year. And it did finally bite the dust. And so I'm going to show you all why that happened, how you can avoid that for your own, and how you might be able to upgrade and repair this thing in some cool ways. So that's, and by the way, Fairywill is the brand of this one, but there's a lot of, you just look at the design style, there's a lot of these, and I'll show you, I'll talk about the parent company that actually designed it. It was not Fairywill. And so what I've got here is some of the parts here, and these were really gross. I've actually steam cleaned all of these. What I'm doing now is actually quite possibly fixing the thing that actually broke, that led to this leaking on the inside. Because what happened was one of the seals became disconnected. Here's the reservoir chamber, of course. And where did I put it might be in the other room, the actual part with the buttons on it. I will go get that. But there's a circuit board inside of it, of course. How else is it going to operate? And I'll talk a little bit about, how it works. So you have here a standard, what is most likely a 3-volt motor. There's no writing on it, so hard to tell, but I'm going to test this out on my bench supply. And that goes to this gear, which is, I'm not a mechanical engineer, but I do have some common sense, I guess you could say, about it. And it's pretty cool to see that it's an off-center gear. It has this piece that's off-center on purpose. You might be like, why is that? Usually things are centered on gears. Aha, well, here's the cool thing. That goes into this piece here, which probably goes the other way around. Yep. And this is how we get our, let me actually go ahead and just assemble this in its original state, like so. So when this gear turns, because it's off center, it's going to pull and push up into this chamber here. And that pull and push action, you can see the 2 O-rings there, which create a water seal, watertight seal. It's just going to do that, right? And so that goes to this intake valve, which is basically intake. I don't know if you would call it. Like I said, I'm not a mechanical engineer, so forgive me if I don't know all the terminology. But that goes to that intake there, which is connected to, let me zoom out just a little bit. Connected to this dude, your little hose here, and this goes in your chamber, in your water reservoir chamber. It goes through the top there. And so it's really cool. So, and this by the way is sort of a crude filter that it has to keep out particles. And so yeah, what it's doing is it's doing this push and pull action over and over again. And so it's when it pulls, it's going to create suction in here, which sucks up liquid water, and in my case, a little bit of mouthwash through there. And then when it pushes, it's going to come out the top, out the spout here. And I think the reason it's not going to come out here is because there's actually this weird little filter in there, this orange little flange filter there. And I guess that helps keep it unidirectional. And so, yeah, there's a little, like, what looks to be some kind of fancy C-clip here holding this in. And what else can we say about it? It's a really cool little mechanical design. And, you know, the crux of anything like this is going to be the mechanical design. The electronics are simply secondary. But it's got some nice, you know, watertight seals on here, and everything's looking fairly good. So, what happened? You know, how did mine break? We've got seals on everything. You know, the bottom case is here, is all sealed. And there is a battery, which I might show later. It's in the other room right now. There's a little lithium-ion battery in there. And then there's also a circuit board, which goes like that or something. Yeah, it does. It's actually soldered to the motor through these two contacts here. So actually the circuit board's mounted like so. And there was water everywhere in here. You can even see some of it's on the motor. It was coating the circuit board. And the circuit board was disgusting. And I had to do a lot of cleaning work to get it back to this sort of condition. And that's, of course, what broke it. Fortunately, they had the wherewithal to seal the battery. So the battery didn't, like, you know, explode or something. But they did not seal the board. And that is the first upgrade that I will talk about. But I'm going to talk about it in a little bit. First, I want to talk about what actually broke. And in my case, I believe what seems to have happened is one of the screws, these very, very tiny wood screws that hold in this seal for the pumping action, one of them came out. And I'm not sure why or how or where it went. But it sure wasn't there when I opened this up. And so in trying to figure out the size of that tiny, tiny screw, I'm using this awesome mini wood screw set that's M1 to M1.7. And it would appear that what it is most likely a 1.4 or 1.5 6 millimeter screw. And what I'm doing is I'm actually comparing the original screw on the right side under my microscope with the one that I'm getting from this kit, so I can match the threading and, you know, hopefully length. And that's a pretty close match. It's a M1.4 by 5 millimeter. I'm going to try the M1.5 by 6 millimeter, and I think I'm feeling pretty optimistic about that. The reason we want a wood screw is because it's self-tapping into the plastic, and that's kind of the difference you'll find largely between wood screws and machine screws, is that sharpened point. And if you're watching this video, you're probably already familiar with that, but, you know, doesn't hurt to mention it. And so, yeah, oh my gosh, that looks perfect, actually. So this is a 1.5 by 6 millimeter, and I think that's our guy. We're going to go with that. So I have my replacement screw, since I don't know what happened to the original when this thing broke. And now we can go over the electronics a little bit. And I'm going to go ahead and see if I can get a slightly better view on the monitor here. Not too bad. My new camera mount. And we're going to take a look at our trusty circuit board and kind of a little rundown of what's going on. And so we've got Segasonicfan is actually the manufacturer of this board. Not only this board and kind of all of these units, I think, but what's kind of cool is they have their own branded IC. And this is the brains of it, the Segasonicfan F5012. And then 1024 is probably the size of the flash memory, I'm guessing. And there you go. It's a combination microcontroller. I guess that's really all it is. Just a microcontroller in an SO, what is that? 3, 4, 5, 6, 8, SO14 package. And what's weird is I believe that guy is the power pin. So it's got, you know, these chips that come out of China that are customized, that are developed over there for budget consumer goods, are often really funky pinouts without a lot of information online because, you know, they're not meant to be like widely distributed. And this one is just funky in the sense that the power pin is, I don't even think it's the middle pin. I think it's, I have to double check. But it was like it's a weird orientation. It's not your standard, like, so, standard for SO14 is you have power pin is the last one. It's usually 14, and then 7 is the ground. Not the case here. But we've got here our little, microcontroller, and I'll go over more of this stuff in detail in a bit. We've got here a charging circuit. The charging circuit is actually an off-the-shelf, also really common out of China, and just the Eastern electronics world, which is the TP4056. TP4056, you've seen these little modules for Arduino, most likely. They're very, very common for hobbyists to do charging, and for a single cell lithium ion. I don't like this chip. In fact, I will bluntly say that I think it's garbage. But it does the job in most scenarios. Why do I think it's garbage? One, it produces a tremendous amount of heat dissipation for what it's actually doing. It's nowhere near as good as the stuff that TI produces and such, but the BQ series. But it is very, very affordable. You can't beat the price. It's also does not do load sharing, which means if you're charging it while you're using an item, it will not kind of do those two processes simultaneously, and could potentially damage your battery by always charging it when it's plugged in, since it won't know the off state if there's a load applied. So it doesn't measure like output load or anything like that. To do that, you need an output MOSFET control circuit. There's a great article on this. If I can find it, I'll try to link it below, about the importance of load sharing when you're designing lithium-ion charging circuits. So it's not like something I would use, for example, in one of my designs. I've never used this in one of my designs. It's really, really budget. There is a newer version, actually, of these that do 2-cell lithium-ion batteries. I don't think they're produced by the same company. They are starting to take over this chip, which is good, because I think anything to replace this one would be nice. But like I said, it does do the job under most conditions. And in fact, it was not the point of failure. It was liquid damage. That was the point of failure. So, can't blame it too much, I guess. We do have a large decoupling cap. We have a couple of LEDs here to give charge state and the current mode selected. This resistor and this capacitor, I believe, are helping to determine the charge current. And I believe the charge current is very, very low when you have this 2.2. I feel like, I don't know what, 242? I think that probably means it's could be a 200K, but I don't think so, or 20K. Well, we could just take a reading right now. Got my meter right here. Not up to speed on all the different SMD markings. They seem to change for resistors quite frequently, but let's see what we get. Just so anyone watching is curious. Okay, yeah, it is 2.4K, so it is actually 242. It's just like it says. Sometimes you get letters and stuff in there that confuse it. But yes, we got and I don't have the math in front of me of what the charge current that sets that up. And you can change that, of course, and charge your battery faster if you want. I wouldn't recommend it necessarily. It's going to depend. It's going to rely mostly on trickle charging, I'm sure, because it's a small battery, but could be wrong. And this is a small decoupling cap for the battery. As you can see here, battery plus goes in here, battery minus, and the negative for the charge plug go here. And J plus is actually supposed to indicate, from what I understand, that that's the positive terminal for the charger. Some design flaws you're going to notice right away. First off, holy crap, look at how close these two connectors are. Holy sure. This is negative, this is positive. Power. Bad. Holy crap, is that bad. Second thing you're going to notice is that there's a decoupling cap for the battery input, but there's no fuse. Very bad design. Now, of course, they did this to save money, but it really sucks when you just have a decoupling cap there, because if this cap shorts, it's no good. There's the built-in protection board under the battery, which is glued into place. If I can get to that later, I'll show you. But it doesn't save your board here. It just means your battery hopefully won't catch fire. So yeah, this scenario though is pretty gross. It's pretty bad. And then you've got your motor which actually solders to the motor directly, which is cool because the motor then will double as a PCB board mount, which is a really nice space-saving design. I really like that. Got a lot of through-hole vias just to do heat dissipation in the power planes. Good design, good technique. And then we've got some resistors here for, again, one more LED indicator, and some pull-down and pull-up resistors for the MOSFETs, which I'll go over in a second. Likely MOSFETs. Got, of course, the board revision and design 2018 is when this was originally developed. And then we've got, of course, our simple tactile push buttons. On the back, we've got, there's a decoupling cap that I removed here because it was destroyed by the liquid damage. This is your decoupling cap for the chip. First design flaw with this guy is your decoupling cap for your microcontroller should always be as close to the chip's power pins as possible. It really defeats the purpose when it's far away, especially when it's like almost an inch away like this. The whole point of having what is most likely a 100 nanofarad, 0.1 picofarad capacitor here is to reduce high frequency oscillations, and this trace length will introduce that. So kind of engineering 101 kind of mistake there, but not the end of the world. It will still do the job. It will still reject other voltage ripple most likely. And then you've got here your two, what is probably MOSFETs, which are of course doing like is it an H bridge? It's not an H bridge configuration unless there's two others, which maybe are inside the chip. Oh, but it doesn't need an H bridge because it's not ever going in reverse. Okay, so yeah, these are just half bridge. It's a half bridge configuration to control the motor in one direction. Here was previously a big large diode, again removed because it was destroyed. That's your feedback diode for the motor. Pretty straightforward. And then of course you've got the pull-up resistors for the MOSFETs for the half bridge. And this 1K is for the gate. That's for the current limiting for the gate on the MOSFET. And what else can we see? We've got these two resistors. I forget what those are for. But it's not terribly complex. The most complicated thing about this, of course, is the microcontroller chip, which is basically just a PWM controller. I'm wondering if it's doing some measurements of the battery voltage as well. I would imagine one of the pins is like an analog in, so that it knows when, to do charge termination and stuff like that. Although the TP4056 will do charge termination on its own, I believe. But I kind of wonder, because I think there is actually both a power input and a sense input. Could be wrong about that for the analog in. But regardless, it's not super important because we can always incorporate that in our design anyway. We should. It's a good idea. And what can we say here? Yeah, I should probably look for a voltage divider with two resistors, which might be what this is. Going to a pin, and going to the power rail, which would indicate, oh, that is what this is. Yeah, so totally. I just found it. So yeah, here's our power input. You can see it splits here to go to this capacitor, this whole set of parts, which is unpopulated. And then goes here to the power pin, which I think actually is this pin. I think it's pin 10. And then it goes to our to a pull down and a pull up resistor to what is presumably an analog in to measure the voltage. So yeah, it is doing it is going to a sense input from what I can tell, because that circuit's not going anywhere else. So yeah, so it's measuring your battery voltage, probably doing some kind of monitoring stuff for that, and then of course it's doing doing switching for the MOSFETs to turn the motor on and off. And depending on the amount of button presses that you make, it will change the PWM duty cycle. So that will, of course, make the water kind of splash differently and stuff in your mouth, which is pretty cool. But there's only one setting I've ever used, which is typically the strongest setting. And what the fun thing is, if I'm making my own, I can kind of experiment with what setting, you know, what duty cycle I find the easiest. But yeah, it's very simple. I mean, it's essentially like, you know, like a astable multi-vibrator, you know, like a 555 or something, possibly with a simple voltage monitor for the battery, and then soft starting. So soft starting, which, you know, if you're really talking about like bare bones logic, you're looking at a flip flop, you know, a 7474 with a debounce, which is 74 HC14, 7414 basically. So you got, you know, if you were to, you could actually make this entire circuit out of off-the-shelf logic using like 4 fairly small chips. Wouldn't be that hard. That's how simple this microcontroller is, which is cool. So and that's why it's budget. That's why they're able to do it themselves and not have to, you know, rely on somebody else's part, which maximizes, you know, lowers overhead cost, yada yada. And so yeah, that's our circuit. And so since my microcontroller, it appears to be totally blown. The TP4056 was totally blown. I mean, everything was just destroyed when all the liquid got in there. What I'm thinking of doing, of course, is just having my own PCB in here, or better yet, maybe even just making one external. And I don't want to spend too much time on this project because this whole item costs $30 or less. But I do want to use one in the next day or two while I'm waiting for a replacement to come in the mail. So I might rig up something quite simple and share that with you all later. And yeah, I'm thinking the way to do this would actually be, because the only thing that really it relies on electronically to be sort of near your mouth and exposed to water is this motor. And what I could probably very easily do is just have 2 wires coming out this thing. I'll have to seal it, of course. When I have those 2 wires come out, I'll probably just drill a hole, and I could use some caulking sealant or something like that. The other thing which I'll do when I get a new one of these, because I have a replacement coming in the mail, is using conformal coating, which is really what they should have done in the first place. Now, I'll have to cover up the buttons when I do the conformal coating. But conformal coating, for those that are maybe new to this, is it's a type of sealant that you can put on circuit boards. That makes them moisture resistant. And that's kind of a no-brainer when you're making a water, you know, a mouth irrigator that's, you know, probably going to get liquid in here at some point. But, you know, low cost consumer product. I don't think they cared that much, you know, using a budget charger, budget IC. And this is where you really got to give credit, though, to, I mean, not that specifically, but where you do have to give credit to these engineers in Shenzhen is, you know, at the end of the day, they made a fairly robust, you know, I used this for almost a year before it broke, right? So a fairly robust, extremely affordable, off-the-shelf, mostly, right? This one's custom, but only because it's cheap to make. But mostly off-the-shelf design, simply engineered with a few minor flaws, you know, a couple safety corners cut, like missing the fuse and the conformal coating. But, you know, overall, like, it does the job. It's cheap. It works remarkably well. And so, of course, you know, if I were to design this, I would make a couple of these small improvements. But, you know, I'm not them. So, yeah, just want to say, like, I'm still very impressed with this product. Obviously, the mechanical engineering is much better than the electrical engineering, I would say. Again, I'm not a mechanical engineer, but I think it's pretty darn good. And I'm quite impressed with it. So, yeah, I'm going to put those 2 screws in. I'm going to see if it'll actually create a watertight seal, run those 2 wires out. I'm thinking I might actually just go with an ESP32 because it's already 3.3 volt logic, which I'm sure this circuit, this motor, I'm almost positive it's going to be 3.3 volt, more easy to run it off the battery since I have an ESP32 board with a battery charger built in. And that might just be a really simple way to do this. I'm trying to do this as quick and dirty as fast as possible so I can start flossing my teeth, essentially. Water flossing my teeth. Hopefully this video was useful to you. I'll probably have a part 2 when I finish some more hacking with this. Please leave a little note or something if you liked and you learned from this, because I just like helping people and I love hearing from you. That's it for this one. Segasonicfan, signing out. Hey folks, Segasonicfan back here for part 2 of my oral irrigator water flosser hacker repair thing. Interesting update on the part that actually broke. So it was the screw holding in, there's two screws holding in the, this is the intake valve, which goes to our little intake hose. And one of these screws, so there's a fair amount of pressure when it's, doing its thing. And one of the screws, the head of the screw broke off. Crazy stuff. So if you zoom in here, you'll see I had to kind of drill out the actual metal screw that was in here before, which was, I believe, a 1.7 millimeter M1.7. I replaced it with an M2, which is slightly larger, so that was able to thread in there. Whether or not that's going to hold, I don't know. If I really cared, I'd put some epoxy on this, and I might do it later if I feel like it. But right now, I just want to get a proof of concept going. But the head of the screw had broken off, and so, like, the body of the screw was still in there with the metal threads. It was ridiculous. Wow. I'm not even sure how that would have happened except through pressure, but still, that's crazy. Maybe cheap screws. Anyway, I've got that all squared away, at least for now, with the functioning proof of concept. I believe it's going to be fine for those purposes. We've got some silicone grease on here. I might add a little extra to keep it working later, but I'm not super worried about the greasing of the gear right now. And I'm going to go ahead and put this into place and see if it fits well with that M2. I think it should be okay. Looks like there's a fair amount of space, actually. Oh, yeah, it actually comes out the other side, so that'll be fine. And I thought I'd show just a demonstration of, kind of what this looks like, how it works. It's kind of cool. Let's go ahead and just solder a couple wires on here. This is going to my bench supply. I'm just going to give this motor 3 volts. Nothing too fancy. And go ahead. We can even put the frame on if we want. Like so. And apply power. Yeah. And you hear it going. I can feel the air suction in here. Let's go ahead and get a look-see. Of course, I have to hold the motor down in place or it's not going to make contact with the gears here. Let's see what happens. And so, yeah, just like I was saying, it moves this guy up and down, up and down, up and down, really fast. It's a pretty cool looking motion. And that's all there is to it. Suction here, due to that one little valve cover, that little thin cover in there, makes it unidirectional. And then out there. So I actually only use this on the highest setting anyway. I might not even bother. Honestly, I'm just trying to hack this really quickly. I might not even bother with a PWM controller. I could literally hook this up to a 3.3 volt step down converter, plug that into USB, maybe make an on and off switch, and have this functioning again. At least for the time being, while I'm waiting for my other in the mail. So I can keep up my oral hygiene. Woo! Alright, I'm going to give that a shot. We'll see what happens. More to come in part 3. Hey folks, looks like my crazy microcontroller hack is going to have to wait because I've actually repaired this this water flosser circuit board, which is kind of amazing given how much water damage it was taken on. And I'm going to talk about what I did to repair it because it's kind of funky. And I'll have a question for you all, so watch till the end. Just got the board under my microscope. If you haven't seen the previous video, I guess I could hold it up here. This is the board, and let's get some light on it. That's inside the water flosser, and what basically happened is kind of interesting. There are some exposed pieces of copper above the substrate that don't have solder mask on them. And normally that's reserved for, like, pads, like here. However, in some cases, it's just for large vias that don't have masking on them, like this one, which actually goes to the flyback diode. However, over here, you can see I added a bunch of solder and a little janky wire here. This is not fancy work at all. This is super patchwork on a super cheap budget item. So I'm just doing some testing here, but this bridged, there was an exposed pad here that I bridged and connected this 100 ohm resistor to the LEDs down here, as well as the power going to the microcontroller. And so when I bridged that, it connected to the power rail here on the microcontroller. And I also, added this. I just chose a 10 microfarad capacitor just to give it some bulk to it. It probably is a 0.1 microfarad, but anyway, that's just what I did, just to try to see what I could get out of this thing, if I can get it working again. And so, yeah, I did that, and then I also replaced these N-channel FETs. By the way, it's two N-channel FETs connected in parallel, and it's really simple. Basically, I believe it's this pin. I think it's pin 6 over here on the Ryzen chip. Goes to a 1K current limiting resistor, which then goes to the gate of both FETs in parallel. You can see the two vias here that connect them. And then there's 100K across the gate to the source, very common. The source is, of course, ground, and then the drain is the two pins here connected together, which then go to your flyback diode, as typical FET switching circuit. So my previous video, I was like, oh, maybe there's a half bridge or something. No, all they did was they just connected two MOSFETs in parallel to increase the current output. And I would almost guess that they used like a 2N7002, but I don't know for sure. That's what I threw in here because I'm assuming the original ones were broken, since the flyback diode was indeed completely broken. And so that still did not fix it. And the symptom I was getting was really interesting. I'd press the power button, to start it and measure with my oscilloscope on the gate here, because that's really the way to do this, and see if it's getting that PWM pulse. And on my oscilloscope, I would get a single pulse, just one. It's really interesting, because if the microcontroller was totally dead, why would it give me one pulse like that? That's a really weird failure state. Normally, either the soft start circuitry wouldn't work, or the internal oscillator wouldn't work, or something like that. But to see a single pulse like that had me scratching my head. So lastly, I went back to this voltage divider circuit here, because this is like the last thing to really check. There's not a lot else going on with this chip. Obviously, it's sensing the button because it would give me a pulse. Obviously, it's outputting something because it gave me a pulse. And it actually blinked the LED once. So it's trying, and it's getting power. So I tried the bulk capacitor at the input, just to make sure it wasn't a power issue. But yeah, all that was left was this voltage divider circuit. This voltage divider circuit is really confusing. And this is where I need your input, if you feel like providing it. Because I looked up the resistor codes for these SMD resistors, and they use the EIA-96 standard of codes, which is, I guess, a more becoming increasingly popular, it's really weird. Basically, the first two digits represent the three first significant digits through basically like a decryption table. The first two digits are just code for actually 3 digits. And then the third digit, which is a letter, is a multiplier. And in this case, 64 actually means 453 with a multiplier of 1,000, which comes out to 453,000. So it's 0.453 mega ohms, which is what this measures. And then over here, this I just threw this off to the side. This is what originally was above this guy. And it's really hard to make out because it's so small. I don't think it's a 6 because it looks really different from this one. And I don't think it's 006, although I suppose that's possible. They did not use an EIA-96 like they did for this code. So I guess it's very possible that was actually originally 006. But to me, it was almost like it was upside down, and it's actually 90D. And if it's 90D, it's actually a very, very high resistance. But I was like, you know what? This is, I'm just going to trust my gut here, which is that this is trying to measure a voltage. And if that resistance, so A, I have no idea why this is so freaking high. And B, I don't know why this is so high. I mean, if both these are so high, like in the, almost a mega ohm, half a mega ohm, really, really high resistance, well then how is it going to measure anything? And I'm thinking, is it trying to measure like if water touches the board or something like that? I mean, maybe. But at the end of the day, it's looking for a voltage. And if I can limit the current in a way that's not going to damage the chip, I can at least see what happens. I'm sure I could bring it up to VCC, which we know is this power rail here, which is, roughly 3.3 to 4 volts or whatever. And so I was like, okay, well, let me bring it up to VCC and see what happens. Well, let me limit the current to be safe. And so I stuck a 100K resistor on there. And after sticking that 100K resistor on here, we press the button. Applying 3.7 volts here, just kind of nominal lithium ion here. And what do you know? We've got our LED and everything seems to work. Very exciting. And so now turns off and on, and I can change modes. Pretty cool, huh? So yeah, not much to it. I guess maybe one of the last things I'll do as part of this weird little repair. I might do actually one more part to this video. You might be thinking, well, how much is he going to talk about this water flosser? I think it's interesting stuff. And by the way, one failure point I'll mention also for those of you out there getting one of these. This plug is quite the failure point. You have to put a little rubber stopper in it. I mean, I guess they did the best they could because they're trying to power it off of 5 volts. And if you do a barrel jack, that's still going to be a failure point too with the liquid. I wish the rubber thing though would like attach and like kind of hang off to the sides. You have to worry about losing it. But you got to really be careful you don't get liquid in there. And then of course that goes these 2 wires, which go to the 2 points I previously showed. What's kind of cool is there's some really decent insulation behind these buttons. That's pretty well designed. I like the membrane insulation they used. It's also very stylish. I think it looks really cool. But yeah, I'll make another video to go over. One is I do want to examine the working pulses on an oscilloscope, just because I think it's interesting and also would make for the possibility of doing a one-to-one copy in a microcontroller, just for, I don't know, if I ever want to. And I'll have to double check the N-channel FETs that I'm using to make sure they have the proper load capacity. I might even put the old ones back in and see if they're actually functioning, but I kind of doubt it, but we'll see. And what else was I going to do? Oh, yes. And then lastly, the most important thing for preventative maintenance and making sure this continues to work is adding conformal coating. Conformal coating, as mentioned in the first part of this series, this video talking about this water flosser, oral irrigator, is to insulate the circuit board from any liquid conductivity, and is really what they should have done in the first place, but didn't, which is why this broke. And so, yeah, then I'll be, of course, putting the gasket kind of through its paces once I get this all put back together too, because I have this little kind of janky repair where I've put an M2 screw, and I could actually hack this and put a nut in the back there, which is really what it should have. These 2 screws here should really be connected to nuts. They're too small to be wood screws, self-tapping wood screws into the plastic. This is obviously taking too much pressure to handle that, at least long term. To be fair, this broke after like a year of use. But yeah, you do these steps and this thing will work, for a really, really long time. It's got a decent battery in there too, like a, I don't know, miniature size, not an 18650, but it's a lithium ion cell. It's got a TP4056, it's okay charger. It's got a protection board on the battery, and motor seems fine. So yeah, if I do these steps, this might actually last a really long time, which would be cool. And this was an excuse to clean it all out and learn some things, so that's nice too. More to come if I decide to make another part to this video. Have fun repairing your water irrigator, oral irrigator water dental flosser. You know what I mean. Ciao. Hey folks, Segasonicfan here, and I'm working over on my little oral Irigator toy. I don't know, toy, useful household item. I love this thing. And it was very broken from liquid damage, and I'm here continuing on my repair, which is more or less now complete. Pretty proud to say it was a bit of a journey to get here, because a lot of stuff was damaged from the liquid, from the water leaking in. And I thought I'd give a little rundown of some of the engineering stuff. I keep finding more stuff that's kind of interesting. I love hacking on these things, these kind of consumer goods from Shenzhen with cool little tricks that people have incorporated. So here I've got it charging right now, although actually I don't have it charging, that's just the on light. This is the charging light, and I presume it's not charging because the battery is at 4.2 volts. And I do have to discharge the battery a bit just to double check that the charger is working. But it's a simple TP, what is it? Blanking on the model again now. 4056, right. Hey folks, I'm back here with my oral Irigator and my water dental flosser repair here. And I thought I'd show a little more of the engineering stuff. I've got it pretty much working now, running off battery, and I just have to check the charger once I discharge the battery a bit, but I think it's going to be fine. It uses a TP4056, which is a really common off-the-shelf budget charging IC. And boy, have I had to replace a lot of stuff in here that got destroyed. So I had to replace the small decoupling capacitor. I just used 100 nanofarad for that, aka 0.1 pico or 0.1 microfarad. You'll see this little weird blob here. That was what happened is the test points. There's some test points for your probes, such as this one. That's a ground test point. But a lot of the test points were junction points between traces. So when the liquid got in here, it corroded the exposed copper of the test point, thus breaking the trace connection. I generally don't use test points as a bridge between traces that have solder masks on them. It's a bad engineering practice, and this is a great reason why. So there's that. I went ahead and patched that test point, essentially that trace there, which is the motor power and the decoupling power here for our charging IC. And then additionally, let's see if I can get I had this under the microscope before, which was nice, but it's a little inconvenient with all the wires hooked up to it. So I'll keep going up here. And then that power line comes up here to another test point, which again was corroded and damaged. So yeah, that's why it's got kind of a solder blob there to kind of fix all that. This also went to, I'm sorry, this is not the test point. This is a through hole, which also goes to the flyback diode for the motor, which I also had to replace. And then that goes to the power rail up here, and you'll see I actually added a resettable fuse. This is for the microcontroller. The microcontroller is the one thing I can't easily replace, and that's what I was really happy to find did not need replacing and was not actually damaged, surprisingly. But to keep that so, I went ahead and put this is a very low rating, 50 milliamp resettable fuse. And I kind of took a gamble on that because I'm thinking this microcontroller is really simple and doesn't have a lot of front end, and it's just a PWM controller that's measuring battery voltage and swapping between 3 different PWM pulses. And that's about all it does. It's not very smart. So since it's pretty much a few logic chips, I figured it could handle that really low fuse, but we'll see. And then this resistor right here, R5, that's actually the brightness. That's the current limiting resistor for the LEDs. They did an interesting design here. It's not terrible, but it's not perfect, which is if you press the button once on the top here, you get your power light. Press it again, you get your mode 1. Press it again, you get mode 2, which is no LEDs. It's actually still on right now. And then you press it again, you go back to mode 1. This last LED is for your charging light, which turns these off and then charges. You might ask, why did they do that? Well, kind of a clever cost-saving technique. If you do things that way, no 2 LEDs are on at the same time. You have 3 LEDs, but they're only on independently, which means you can use one current limiting resistor for all 3 LEDs, which is what they've done, which is kind of cool. What's my gripe about that? Well, I really don't like that mode 2 has no LED on. I think that's kind of weird and confusing, but not a big loss. Anyway, I think that resistor is a little too bright originally. It was a 100 ohm resistor, just too bright. So I changed it to a 1K. It's still plenty bright, and it's not going to blind me when I'm in the bathroom at night. Lastly, we'll take a look on the other side. Of course, we've got our motor terminals, battery terminals. I mentioned before that the charging terminal and the ground are way too close to each other. I really don't like that. You see that little bridge? There's like hardly anything there. I don't know what they were thinking when they did that, but I'll see what I can do about that. Here's the flyback diode that I repaired and replaced. Here's the two replaced MOSFETs. I'm using kind of underpowered 2N7002s. I don't know what they used originally. So again, I'll do a little bit of testing. If I have to put in more powerful MOSFETs, I can do that. Not a big deal. Replaced the decoupling capacitor with a 10 microfarad. That was fine. And then the real fly in the ointment that I really had to figure out was replacing this resistor here. These two resistors make up a voltage divider, and that trace that you see right here is a battery voltage sensing trace. It's kind of cool, actually. They set this microcontroller up so that if there's a problem with the battery, it will not start. And what happened was one of those resistors went bad when everything was shorted with the water damage, and it's over here now. Just kind of dropped it over there. And that made it, of course, not be able to sense the battery. And so the symptom I was getting from that was I would click on, and I would get a single pulse, just one pulse from the PWM output on the gate right here. Just a single doop. So it would like turn on for like a split second and then go off. I'm like, that's interesting. That makes me think there's the microcontroller might still be working, but it's sensing a watchdog situation. And that, of course, is exactly what it was. So now we are all good to go. And one thing to keep in mind is these leads for the motor are a little fragile. I'll go ahead and just do a little demonstration just for a second, just by touching the motor leads here, because I don't want to keep soldering and desoldering them because they're a little fragile. Go ahead and touch the motor leads. And there you go. If I click the mode button, mode 2, mode 3. Like I said, no LED for mode 3. Back to mode 1, and off. So yeah, all seems to work. I just got to double check the charging circuit. Like I said, it's not illuminating right now, I think because the battery's fully charged already. And I don't think it has, I'm certain it doesn't have a charge complete light. I guess I could leave it like this for a few minutes and then go ahead and try to charge it. So yeah, successful repair, feels good. It would have been fun to make a little Arduino project to recreate that microcontroller, but no need to. And what I'm going to do now is, so I upgraded the LED, of course, upgraded it with a protection fuse. I might add another protection fuse for the battery, even though I'm pretty sure it has a fuse on the protection board, but I think it couldn't hurt to do an inline fuse. And then lastly, what I'm going to do is I'm going to cover up these two buttons with some tape and then conformal coat this. It would be kind of fun. I haven't done conformal coating before, and that is a way to electrically isolate from liquid this PCB. And it's a transparent process, so the LEDs will still shine through. I'll still be able to see parts, and if I need to do repairs, I can scrape away the conformal coating later, as I've done on boards previously. And can take a little bit of resistance. And then, of course, I'll have to double check the mechanics of the pump action, but I'm pretty sure that should be fine. There was just that one screw that came loose, essentially, and I can always epoxy things if I absolutely have to. All right, thanks for checking this out. I might do one more video with it all put back together, but you get the gist. Segasonicfan signing out. All right, folks, so I'm back here, and I have protected my PCB. You know, I was so excited to finally use conformal coating. I had a couple cans for it that had been sitting around my workspace for years now. Like, God, I want to say like 5 years or something. I hadn't had a use for it. But then I couldn't find it. The one time I finally needed it, I couldn't find it. So I cheated, and I used just some paint enamel, some fast-drying interior-exterior paint enamel. It's not made for plastics, but I somehow doubt it's conductive. And it is designed to help, you know, repel liquid. That's kind of what that's for. So I think it'll be just fine. And I'll do some tests, of course, but just showing under the microscope, I put some polyamide tape to cover up the buttons. Didn't want to get the paint in there. And, you know, I could have covered up the LEDs. They might get a little bit frosted, kind of diffused appearance. I'm okay with that. No biggie. You see it coated the board pretty well. Maybe there's a spot by the charger that it didn't get, but I don't think so. And by the way, I should note here, you'll notice the wires here. This was very annoying. It turns out the microcontroller by default shuts down the chip enable pin for the charge circuit, the TP4056. Why it does that, I don't know. They kind of did some silly things. Basically, how this is configured by default is this LED is actually controlled by the microcontroller. And I think what they wanted to do was have a blinking blue LED. Or why they needed to blink to show that it's charging, I don't know. They could have just made it a red LED. Maybe it was to reduce BOM costs so that all the LEDs could be blue and then you would know this is the charge one. I don't know. They could have just, they also have it, they could just label it charging or whatever too. But in any case, maybe it's a dual purpose because it's also supposed to be for a massage LED. In any case, it's now a red LED, and there is no massage LED that works anyway. And this is now just configured like a really standard TP4056 configuration. It still has the same like low charging current, which I like. I think it's like I can't see the resistor under here, but it's fairly low charging current, which is good. It's a small battery. But then I've tied the chip enable pin, which is pin 8, over to the power pin, which is pin 4, I believe. And then what else did I do? Oh yeah, and then for the LED, I isolated both ends of the LED, tied one of them to 5 volts in, and then the other one has a 1K resistor going to pin 7, which is the LED charge indicator. So then that'll be pulled low when it is charging. It's floating or high when it's not. By default, this has that pin not enabled by tying it to ground. And then pin 7 actually communicates with the microcontroller because that's also usually an LED active low. But yeah, why it controls the chip enable pin, why they actually want to not have the chip enabled, I don't know. It's a very, very low current when it's not being used. But that's just how they did it. So yeah, I decided to just kind of do those wires instead of trying to figure out the what I believe it's probably controlled. Probably a lot of this stuff is determined by that damaged voltage divider circuit here that I explained earlier, where I replaced this resistor with 100K. But trying to figure out why they decided to do all that when it's totally not necessary. I figured just have this be a standalone charging circuit, let it do its own thing. Doesn't need to communicate with the microcontroller, especially because it's not using the TS pin, which is pin 1, to do any kind of thermal regulation. It's not doing any of that. So yeah, it's in a standalone standard TP4056 configuration, and the microcontroller does what the microcontroller does. And so yeah, it should all be good. It's all conformal coated. Paint enamel coated, I should say. And I covered up the motor contacts as well. So then those will be hopefully fairly easy to solder. Let's go ahead and remove the buttons here, and they look fine. Looks like the tape did its job. And yeah, I think this will be good. So I'm going to put this all back together and show some results. Oh, and last thing before I do that, though, I should just show what I did do also a little differently before I did all this paint stuff, was I soldered in to the contacts some JST plugs. These are JST PH 2-pin 2.0 millimeter plugs. And that way I can just leave those wires soldered in with the paint on them or whatever, and I can plug and unplug the battery and the charging port as needed. More to come after these messages. All right, and here I am back with everything all assembled. I'm just going to solder these 2 wires to the charging port, but everything looks pretty good. And I actually put a little bit of water from, had the little tube go down into the chamber and shot a little bit of water out. In fact, it still shoots water out. But yeah, there you go. It turns on, and everything's good. So we'll see if there's any other kinks. I did, in addition to the M2 screw to fix, that was a problem. Just to reiterate, the whole reason this broke is that this screw head actually broke off completely, the previous screw head there, and then water seeped in all down in here and then got all over the motherboard, which had no protective coating, so it fried almost everything. And so yeah, what I've upgraded now is it has a red LED charging light instead of an annoying blinking blue one, and lower resistance for the LEDs. They're not quite so bright. It's now got charging, it's got disconnect plugs for the battery and for the charging port. And that's about it. Didn't do a ton of upgrades to this, just wanted to get it working mostly. Oh, and so yeah, I replaced that bad screw with an M2 instead of a M1.7 or whatever it is. And then I also put around the, because I had to drill out the old one, so I put some Loctite Premium 3X, which is kind of a liquid nails adhesive around that to hopefully form a pretty good seal around there. And yeah, we'll see if this holds up. All right, folks, I'm very happy to report that our buddy, the Water Flosser Oral Irigator, works once again. And it will spray everywhere, but I guess I could do it for a second. Yeah, there you go. So, yeah, nice and powerful, just like stock. In fact, maybe even a little better. I replaced the blown MOSFETs in here, which, by the way, are very nice N-channel MOSFETs. They are SI2300DS MOSFETs from Vishay. They're N-channel 30-volt MOSFETs rated at 3 amps of typical current and 68 milliohms, respectively, of RDS on, which is the on resistance. So you want to get a MOSFET that matches that or better. And I used the DMN3404L, I believe is what I used, which is a 5 amp MOSFET with a 45 milliohm RDS on, I think. And yeah, it does the trick. That was the one thing I had forgotten to change. I had to take it apart to do that. Forgot to put in a better MOSFET because I had used some cheapo N channels for testing. Check it out now. I can go ahead and charge it. You'll see it's got a red charging light. It does not blink blue to make my bathroom look like the mothership is landing, which I really like. And another kind of a nice upgrade, I guess you could say, is if we look at the bottom here, I'll try to do this without spilling water everywhere. And I'll turn on my light here. You can see that there's now 2 plugs, one for the charger and one for the battery, which are easily accessible and can be disconnected when I'm going to service this. Of course, the main upgrade is that the entire board is now coated in paint primer to make it far more resistive to the elements, especially liquids. And yeah, this could be actually working for a good long time to come. That sure would be nice. I mean, all the rubber seals look fine. And it was also a nice excuse to take it all apart and clean it. I steam cleaned all the plastic because it was getting gunky and stuff over the past year. But there you go, a lot of work to fix a $30 item. And you might be like, why did you do that? Well, kids, we learned. And refocus my camera here. We learned new things. We reverse engineered some stuff, figured out how things worked, made it better. And if I ever need to do any kind of motor stuff in the future with water and, I don't know, irrigation type things, I have a little more knowledge under my belt. Also, we saved this from the landfill, which is where this surely would have gone if I had not fixed it. So yeah, have fun cleaning your teeth and keeping up your dental hygiene. I'm now going to eat some candy. Haha, because I don't have to worry about my teeth as much. This is Segasonicfan, signing out.